Okay, so we're going to continue with our review of this course. So what we did last Thursday is I went through lectures 1 to 6 and reduced it down to sort of little snippets of must-know stuff. That notebook you should have access to now, and it's given the title of Review Lectures 1 through 6. I'm just continuing to go through the rest of the lectures. We'll go through hopefully about 6 or so lectures today, trim this course down again, and then I'll post this all the way through. I am recording this lecture, and with this lecture and the previous one, I'll get that up on YouTube as soon as I can, in case you need to see any part of it again. The goal here is to go through the parts of the course and use it as a way of reviewing what we've done and giving you an opportunity to ask any clarifying questions. One of my hopes is to point out things that you do not need to look at anymore. We did a lot of examples of certain kinds of problems. I'm not going to ask you about the specific examples. It's the general techniques and ideas of the course. So to review, what we've covered so far is this basic setup that all the problems we've had have had some sort of driver program that I'm calling an app, some sort of code called a stepper that iterates through the model, and then some code that visualizes the result, a plot of some kind. These are all of the modules which we have been using. So I'm going to start off by importing those as a first step and go back to reviewing simple harmonic motion as an example of an oscillatory scheme. Okay, as we've been doing, I will take a look at the chat from time to time. So if there's anything on that chat, you're welcome to post it there. Even better though, is to turn on a microphone if you've got one and just speak up and interrupt me, because this whole lecture is for your benefit. So make sure it's being useful. Okay, simple harmonic motion. Basically the idea is this concept of periodic. So I'm gonna sort of give a definition of that. Okay. Okay, the whole idea of periodic is something is repeating after a given period t. That's basically what you need to keep in the back of your mind, is that word periodic. We have some examples like a spring mass system. Oh, that's not good. There we go, spring mass system. We don't really care about the details of it. In terms of an equation, spring mass systems can lead to equations of this form where there is a second derivative of acceleration, which depends upon x as your starting point all the way through. So beyond that, this is just a general idea that simple harmonic motion has the structure of something that involves sines and cosines as the answer. All of this stuff, in terms of the details of it, not really important at all. We can get rid of all this kind of stuff. That's good for theory, but not overly important. We can use Euler's method to solve this, but one of the things we discovered when you tried to use Euler's method with a periodic oscillating system is Euler's method does not conserve energy. It is not a good method for solving simple harmonic motion kind of problems, oscillatory problems. So I think all of this example of when we were looking at Euler's method to solve simple harmonic motion, it's not the right kind of code at all to be looking at. So I'm just going to delete that. I will point out that one of the ideas we covered is energy. That's one way of evaluating how these kind of oscillatory motions go. Okay, I'm going to get rid of all this stuff because this is not needed at all. One of the solutions for dealing with an oscillatory motion is to use a different numerical algorithm. One of them we encountered was something called the Euler-Kromer method, otherwise known as the modified Euler method. And the idea of that method as a second numerical method is rather than computing x and v with the old value of x and the old value of v, the big trick is you compute x with the new value of v and v with the old value of v. So what you're doing here is you're updating the position with the new value of velocity. That scheme is something that conserves energy on average. And so it's better for these kind of techniques all the way through. Whether or not we need this particular code to solve it or not, I don't really think so in terms of notes. And the point is, the important point to take away is for this Euler energy, the idea of energy is being conserved all the way through. So in terms of a question, where does how could this appear on a final exam? If you're asked to change an Euler algorithm into an Euler-Kromer algorithm, the point is to recognize that you're going from this set of equations to this set of equations. You're changing how velocity depends upon x. In code, you could write these as code or in mathematics. And one way of assessing whether or not a method is conserving energy is to plot its energy. I would always give you a formula for the energy. The question would just be, how do I actually go about plotting this? And how do I go about changing the code? Another technique we looked at was the Euler-Richardson method, which is a more advanced Runge-Kutta kind of scheme all the way through. And I think the best thing for this Euler-Richardson scheme is to actually cut this out of this lecture, because we're going to revisit it in a few lectures later on. At the end of the day, the big takeaway from this lecture number 7 is there's periodic motion. You have to be able to recognize there is this thing called a period. A period is how long it takes for the cycle or the pattern to repeat exactly. A motion can be periodic and complicated, but periodic just means that it repeats again and again and again. Simple harmonic motion is when you have the second derivative is proportional to the displacement, but you could have general kinds of displacement, and energy is one of the ways we have as classifying it. That's everything about lecture number 7. In lecture number 8, what we did is we looked at not just spring mass systems, but we looked at pendulums as a case study, as an example of a kind of oscillating system. Okay, the details about how a pendulum works, not important. The details in terms of the equation, not important. One of the things we learned was that there's a difference between a physical pendulum, something that has a sine of an angle, and what we typically do in first-year physics, the small angle formula, okay? So I'm gonna simplify this all down so that you're looking at less content all the way through, and basically reduce this whole thing down to just a simple equation, and contrast it with the one that has a small angle formula. What I'm trying to point out is these equations are some variable and its second derivative is proportional to a constant times theta. If this constant wasn't a constant, then you would not have simple harmonic motion going all the way through. All of this other stuff is very specific to springs, and it's just not important for you to sort of measure or take notes of. It's solving these kinds of problems is what the more important of idea is. We had in this lecture the details of how to solve such a problem, so I think we can leave that in. Remember again that whenever you have a second order differential equation, we can rewrite that as a system of first order differential equations. I don't think that's overly important, but here's some code so you can have an example of how this works. So here is an example of a stepper code that solves it using an algorithm. So here's it doing the Euler-Richardson algorithm. We could also write this as the Euler-Kromer algorithm. And the point here is the sine function, this guy right here, this is solving the true physical pendulum problem. It's not solving a simplified version, it's solving the whole one all the way through. So recognize that this is a stepper code. We need to have some plotting code. And in this plotting code, I'm actually showing an example of how to compute the kinetic energy and the potential energy for a pendulum. I would always give you a formula for kinetic energy and a formula for potential energy. Your task would be to take an equation written in mathematical symbols and turn this into the appropriate line of code so that this plot would work. And as before, we had some driving application to run this whole thing, right? So here we are looking at the actual solution of theta, the velocity, that is the rate of change of the position, and then some diagnostic like energy all the way through. That physical pendulum is all we need for this lecture, so I'm going to remove those other sections. One of the things we talked about in here and on the lab associated with this lecture is the ability to identify a period all the way through. And here was some code that showed you how to find the period all the way through. I think the best thing I'm going to do here is I'm going to have a note. Come on, notes. Keyboard is not working for me today, guys. Sorry. Here we go. See lab number 4 for more examples. Okay. In lab number 4, what we did is we actually found the period of some oscillating systems when the amplitude of forcing was not small, and we were able to measure some of these things. I'd encourage you to look at the solutions to that lab. None of the code on how we actually did it, though, is something that I need you to memorize, learn. You can just assume that there are ways of estimating what the period are. And I will remind you that whenever you have a graph like this, you can always estimate the period just by reading it off the graph. You can look at the numbers and be like, okay, that's the period, the distance from just before 4, just before 6. It's a way of checking if your code is working correctly. Okay, none of this is overly important. Whoa, I don't want to get rid of that. Undo cell operation. Okay, the next example we did after talking about physical pendulums is we added in a new piece of motion. We said, well, what happens if you brought in damping into this problem? So the general theme is given some equation like this. This is an equation of motion. It's really telling you what the forces involved are. Acceleration is dependent upon a force of gravity. We can optionally add many more forces to this list if the problem requires it. So we could add a drag force, a force which is proportional to the velocity. It's very similar to drag as projectile motion. The friction force is proportional to the velocity. That's the idea of these friction forces. So in terms of an equation, what we can do is we can write this whole thing down. For the purposes of the notes, I think it's best if I just sort of clean this up and make it a lot tighter. So I'm just going to call a damped harmonic oscillator this equation right now. So the important point is here's the same basic idea where what we've done is we've added a new term to it. You should be able to take an code that looks like, well, this, for example, a simple pendulum stepper, and modify the acceleration so that you can add in a decay term, a drag term, when you're given it. So if I give you the drag term, can I add in what that code happens to look like? I can leave these codes in here as examples, but they don't tend to do very much. I don't think any of this discussion point is relative, nor is the interactive stuff, interactive stuff, interactive stuff, interactive stuff. Okay, so the theme here is number 1, we have an equation of motion. Number 2, we can add decay terms to the equation of motion. The third theme that we can do is, excuse me, the third theme that we can do today is a loud day where I happen to be. It was quiet and it all got louder. Okay, let's try this again. The third theme is we can add a forcing condition to it. So the idea here is we can add one more term that represents someone forcing the system or pushing on it in some way. I don't think any of the, okay, that's the code right there. We can add a forcing term. So the most general idea is you could add any kind of force, any kind of function, which is going to push the system. So now you have something that represents an oscillatory motion, something that represents damping, and something that represents pushing. This is a more general model all the way through. Often, these pushing forces are themselves oscillatory. Think about pushing a child on a swing. You're pushing it with a certain strength, called the amplitude, and you're pushing it at a certain rate. That's the forcing frequency. Together, this gives you an equation of motion for the system. So I'll just reduce this down again so you have less things to read. Okay? And in the most general way of doing it, it's entirely possible that this right here, right? This variable right here, this could actually be some nonlinear function of x, right? As long as it's something depends upon x, it's going to be oscillatory. Things proportional to derivatives of x, velocities, are usually drags, and then other terms are forcing terms. Can you take this equation of motion and create a piece of code that implements that all the way through, right? That's the basic structure. So I'm going to get rid of some of this text because I don't think that's overly important. And I will give you an example of a driven damped oscillator and a plotter and an oscillator of it all the way through. Okay. So all these examples are doing is showing increasingly complex ways of putting equations of motion that are always built up. They're always built up from simple equations with terms added. And what you need to be able to recognize is how to translate this mathematics into the appropriate line of code. Different equations would have different mathematics, different lines of code. I'm going to make this consistent. I don't want anyone to be looking at this later on and getting confused. There's construction going on here. Okay. I don't know if you can hear that thumping, but I apologize. Okay, what do we got? So those are the basic structure of those three things. And then we did some stuff with interactives. We talked a little bit about resonance. Resonance is the idea that when you've got some similarity between the forcing frequency and the natural frequency, interesting things can happen. I don't think I'm going to do anything on resonance on your final exam.
Dr. Munroe?
Yes.
Could you just kindly clarify the difference between natural frequency and forcing frequency, I think is the term that you used?
Right. So let's imagine you have a problem that's got oscillations. Okay, can you see how this equation, if you ignore the damping and you ignore the forcing term, it's a simple harmonic and motion problem.
Yes.
Okay. Whatever is in front of the variable x,
yes,
that is the natural frequency of the system squared.
Okay, which makes sense because x is the change in position of the pendulum as it is. Yes.
And it could be a pendulum, it could be a mass spring system, it could be something else. Generally, whatever's in front of it, it's what the system is going to naturally vibrate at all by itself. If you put it out of equilibrium and you let it go, that's going to be its natural frequency.
Okay.
When you have damping, those natural fluctuations are going to decay in time.
Yes.
Right? Like a normal pendulum eventually comes to rest.
Yes.
Right? But it's also going to be swinging at some point. You can force a system to be any period you want. If you have a pendulum which is swinging back and forth, you don't have to push it at the same period that it's naturally wanting to swing. You could kick that thing twice as fast, 3 times as fast, 1.5 times as slow, right? You can force a system with any frequency you like. This is basically pushing on something as an external force. So that frequency that you're forcing the system at is called the forcing frequency.
Oh, okay. So all of this is just the net motion of a pendulum or an oscillatory body or system, yes, with its natural movement and all other forces that would be opposing it or adding to it.
Exactly. Exactly. So another model would be, imagine you're driving down a car, driving a car down a road. Cars have shocks, which are basically springs.
Yes.
So if you take a car and you were to pull on its bumper and make the car rise up and down, It would vibrate with some natural frequency.
Okay.
Imagine you were driving that car over a bumpy road.
Yes.
It's been washed out, so it goes bump, 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 bump.
Yes.
Depending on how fast you're driving, that'll set the frequency of how quickly you're bumping your car.
Okay.
Right? And it's completely independent from the natural frequency of the springs and the shocks of your car.
Yeah. Yes, which makes sense because it doesn't have to.
Yeah. Now, if you happen to be in that unlucky situation that you're hitting the bumps on the road at exactly the same frequency that the springs naturally want to oscillate, it's a very uncomfortable ride. Yeah. Right? So that's the idea of resonance. But these are how we're playing with these systems. So oscillatory systems in general have some term which is trying to restore it back to equilibrium.
Yes.
Okay, that's an important part about what makes it oscillatory. The fact there's a negative sign here.
Okay.
They can have terms that are damping terms that try to slow them down, and they can have forcing terms.
Okay.
We could put anything we want in these equations, but if it had that general sense, it would behave dynamically. It would behave in an oscillatory manner.
Okay. All right. Thank you very much.
Okay, no problem at all. Okay, then we took a side trip and we talked about this guy. His name is Edward Lorenz, and he's associated with the idea of chaos. There's very little from this lecture I want you to take away in. We talked about a model of his. I don't care. We talked about the difference between weather and climate. Not important. We talked about Lorenz's weather model. Don't care. We talked about this picture. And the important thing about this picture is if you remember back to when I talked about Ed Lorenz's work, he was writing a model that simulated weather, and he noticed that if he took the same program and he ran the program once, the program got printed out on typewriter paper. If he typed those numbers in and ran it again, the system behaved differently after a while. And the reason was because when he printed it out, he lost some of the digits in precision that should not have mattered physically. This is basically the discovery of chaos. Two nearly identical initial conditions lead to very different long-term behavior. That's the definition. Sensitive dependence on initial conditions everywhere in the domain. That's what I'm giving you as an operational definition of chaos, of a chaotic system. Chaos does not mean complicated. Chaos does not mean lots of fluctuations. Chaos doesn't even mean random. So coin flipping, right? Flipping a coin is a random process. That's not chaotic. It's just random. Chaotic means two solutions in a system of equations that start off with very close initial conditions, close as in they're literally close together, will eventually diverge and become completely different. A random process will start being different. If you had a random process, something like flipping coins, then they wouldn't be the same for a little while. They'd be different right from the beginning. So that's what a chaotic system is there is structure. It's just not always the same. So with that idea, the sensitive dependence on initial conditions, okay, I'm going to actually change this. And give that the name of, I'm going to call that chaotic as an operational definition. Now, the only thing we did with this example is we actually did write down some equations and we solved Lorenz's model and we got what's called the strange attractor. So this is something we looked at as a case in point. So there is a plot of one of the values as a function of time, and you see there's structure in it. But the point is, if you started off the model at -10, if it wasn't exactly -10, if it was -10.00001, eventually it would have a completely different history throughout time. One of the things that is interesting and people like to draw pictures of is this idea of the Lorentz attractor, this shape. The system's always going around. It's a nice way of representing visually a chaotic system. However, nothing about 3D plots or strange attractors is going to occur on your final exam. So I'm taking that out of these notes. I'll leave this in as yet another example of how to take a system of equations, something completely new. Can you take the system of equations and fill in the stepper of a body of code applying a certain numerical method, right? And there's always a stepper, there's always a plotter, and there's always some app to make it work. And we'll just uncomment this for the purposes of demonstration. What you see is this is an example of chaos. Two solutions that both start the same. One starting at 1.000, one's pointing at 1.001. For a while they're the same, and then eventually become fundamentally different. That means you're dealing with a chaotic solution, or the problem is the system is chaotic, or it's in a chaotic regime. Those are always all ways of saying it. And that's it for oscillatory motion. Okay, so what we've done is I've just gone through the important bits of oscillatory systems. They're just more complicated ways of doing it. Euler's method is not always enough. We talked about how energy, potential and kinetic energy, is a way of diagnosing a system. And we talked about the words periodic and the words chaotic. That's the takeaway from those three lectures. Is there anything from those three lectures that we should discuss further? Okay. 7, 8, 9. We are halfway done through the course. Up to this point of the course, we were solving systems of equations that were almost always based on Newton's laws of motion. They don't have to be based on Newton's laws of motion. Numerical methods apply on other things. And one of the things they apply to is numerically differentiating and integrating things. So we talked a little bit about numerical differentiation and integration. This is a topic that I did not put on test number 2, but I definitely am going to put on the final exam. So don't ignore it just because we didn't get to it on the term test. The idea is, how do I estimate a derivative without knowing the formula? I don't care if you can take derivatives from calculus class. I care if you know how to calculate this derivative numerically. The example isn't important. This is the important idea, the definition of a derivative. And then we went through some specific examples of it. I'm going to clean these notes up. Okay, and really get to this idea of different derivative schemes. There is more than one way of approximating a derivative. A derivative, the rate of change of some function, can be approximated with one of many different schemes. The schemes that you need to know are the words forward difference, backward difference, and center difference. Those are the three that I expect. If I say use a backward difference formula, you will implement a backward difference formula. There are other schemes out there. For example, here's a 5-point formula. I'm not assuming you know any of those other schemes, so I will just get rid of that from these notes so it's not confusing in any way. Here are different schemes you could use to approximate a derivative. Derivatives can be approximated from data, as in if you had the information in a table or a data frame, then you could apply one or more of these formula to calculate the derivatives of it. So if I had your data in time and velocity, I could use any of these schemes to figure out the acceleration of that data. There is some details on how to store data. None of that is overly, well, wait a second, maybe I deleted too much there. Do I have my data somewhere? I lost it. Oh well, we'll be fine. We'll be fine. We'll make it up again. Here, I'll do this. One of the ways of storing data is to just make lists out of it. 3, 0.4, 0.5, 0.6. What do I got here? 3.0, 3.5, 3.8, 2.6, 2.8, 1.4. Okay, there we go. One of the ways we've been dealing with data is to group it together into what's called a pandas data frame. And this is exactly how we've been passing data back when we've been using our stepper. So that's the idea, just to clean this all up. Oh, that's weird. Right, there we go. So this is sort of the method we've been using for storing our data. It's the same way we've been storing the results from any of our numerical simulations, that you can always put things in data frames where the columns have names all the way through. So using data frames, creating data frames, something we've covered in the course. You can use any of these numerical schemes to calculate a derivative. So I have some examples here of how to calculate an acceleration with a function, and then I could plot that. Well, the plotting's not overly important, but I think I can leave all this code here as good examples for review. Besides calculating derivatives of data, that is something that comes to you as a tabular form, we also can calculate the derivatives if we knew a functional form. So if you start with the data, you don't know its values at specific points, but you had a formula that you could compute something with. So here is a formula, like JV is a formula, a function that you compute. Then you also could compute derivatives of those formulas. So I think the best way of explaining that is I'm just going to turn this. I'm going to get rid of that example. I'll leave it as some notes. And I'll say this. Be able to compute Yeah, I think this is the right way of saying that particular phrase, right? So the idea here is, let's say you have some function. So let's say you had some function. I think this is something we did in the lab or an assignment. We've done something like this. If the function was okay, do you agree that that is a function? This is the function x cubed plus 2x plus e to the x. Your goal all right, we'll just turn this into something. There we go. So there's sort of the thing is, can you, given some function, write some code that will return back the derivative of this function for any specific value? And I'll even be more explicit about it here.
Dr. Munroe?
Yes.
So in the final exam, for example, would there be a question wherein we're asked to find the derivative of a function numerically as a Python function versus as a SymPy function, for example? Like NumPy versus SymPy. Yeah.
Yes. That is a very good point, right? Because SymPy lets you evaluate something symbolically. Yes. This is letting you evaluate something numerically.
Okay. So that
Yes.
is something to be expected.
Yes.
All right.
That is
Thank you.
very fair sort of structure, right?
All right.
Right. So this is understanding what it means to compute a numerical derivative, right? Yes, you know how to, by pen and paper, take that derivative, but that's not the point. It's something that you evaluate with these themes. Okay, derivatives was 1/2, and the reason we're doing this is these derivatives lead towards numerical methods. The other thing we looked at was numerical integration. Numerical integration, the idea of taking integrals, is all based on evaluating a sum. All that an integral is the sum of some function. We often think about it as the area under the curve, so you can think about the area under the curve as being broken up into a bunch of different shapes. One of those shapes is a rectangle, which means the area under the curve, the integral, can be broken up into this sum. This is what we call a rectangular rule. You don't have to break things up into rectangles. You can break them up into trapezoids. If it's a trapezoid, here, I don't really care what this example is. All this stuff is just examples. All right, so here is some code which implements the numerical integral of a given function. So if f is some function, like g of x, it's something that you could evaluate. This code will evaluate the integral from a to b of that function if the function, the interval is divided up into n different pieces. And here's an example of calling that. I'm passing what's called a lambda function. It doesn't have to be a lambda function. In fact, lambda functions might make life more confusing. So let's do it this way. I'll just say g of y return 3 times y squared plus y. There, we'll do that as the cleanest way of explaining that. There's an example of how to numerically integrate a function, evaluating the function at different points. I'll make a note here, though. Also be able to numerically integrate data in a data frame, say from an experiment, right? One of the things we've looked at is you could load up data, just the table of numbers. If it's a table of numbers, a pandas data frame, then you don't have a function. You have certain rows in that table that you've got to evaluate through. So derivatives, do it two ways. Derivatives of a function or derivatives of a data table. Integrals are the same way. Integrals of a function or integrals of a data table. Be able to do both. We talked about the rectangular rule. We also talked about trapezoid rule. So here is the thinking about trapezoid rule, and here is some code that implements a trapezoid rule all the way through, and an example of it all the way through. Oh, there you go. Integrating data. Here I'm showing you how to integrate data all the way through. Oh, good. I have an example of that. So integrating functions, integrating data. Work through these, type them out, play with them, make sure you understand why the different letters are where they are. What we're doing is we're evaluating this, which is still a trapezoid rule, and you should recognize that that's a trapezoid rule, to evaluate some data when it's described as a table is the important bit. Okay, then we had a nice worked example here about comparing trapezoid rule to rectangular rule. This has to do with error and understanding the error of these things. I think we can safely get rid of all of that for the purposes of reviewing the course. Trapezoid rule is better than rectangular rule. You looked at this in the lab, but I don't think I'm going to ask anything about you necessarily in the exam on convergence rates of these different things. So there's two different ways of doing them. These different techniques, these different methods for integrating data, they all come from something called Taylor series. The mathematical theory behind all of this is that any continuous function that's differentiable, smooth, can be written as an infinite series where its terms, infinite power series, where its terms are given by the derivatives at that point. This is what a Taylor series is all the way through. A Taylor series is how we mathematically figure out the error associated with any of these numerical methods we've looked at. Numerical methods for solving systems of ordinary differential equations, numerical methods for evaluating derivatives, numerical methods for doing integrals. It's Taylor series, and Taylor's theorem is the mathematical, does that mathematical heavy lifting to actually prove that, okay? I don't need you to calculate Taylor series. That's something you would do in a calculus course. What I need you to know is to recognize that the reason we introduced Taylor series is where these formulas like forward difference come from. The reason we say a forward difference formula, which is what this one is order H, is because this is the formula which is consistent with a Taylor series. Another way of saying that is I could take Taylor series and I could rearrange it to come up with this formula. And the difference between the true derivative, which would go on in a sequence forever, and this approximation, the forward difference, the error, the difference, is some term that's multiplied by H. It's of order or H type thing. So we say that this thing is order H because it comes from the Taylor series, or it's consistent up to order H in the Taylor series, or any language like that is what I'm looking for. We've got some examples here of deriving a forward difference, deriving a backward difference, and deriving a centered difference. I think those are all good things for you to take a look at. We could do a second difference as well, but let's get rid of that as an example. And those are just examples. Okay, so here's the takeaway. So in terms of the mathematical stuff, okay, Taylor series is true in general. Depending on how many orders it's consistent with, we're able to write it down. So if you're able to have something which is accurate to within these first two things, we say that it's an order 1 method. If it's accurate to within the first two, it's an order 2 method. Question from the chat, is the order of the method the degree of the Taylor polynomial used to approximate the function? No. It is the order of a numerical method. If it's equivalent to the Taylor series up to that order, then that's what we say the order of a numerical method is. When you take a numerical method and you actually go through and you solve for what f of x plus h would be from the numerical method, you're going to get a different sequence of terms. It won't be this one. If you got this sequence, then you'd have Taylor series. Different numerical methods will give you a different sequence of terms. And it might terminate or it might not. Probably does terminate. Depending on how many terms it's matching with the Taylor series, that's how we're defining the error. Is that okay? So I will leave these three in here as something that you can do. You can start from a Taylor series and you can prove what the error is of these methods. Okay. We also introduced a more advanced way of solving for the area under a curve, something called Simpson's rule for integration, to point out that you can do better than first order. You actually can do more advanced techniques by using the idea of a Taylor series. Simpson's method is great. Use it in practice all the time. But for the purposes of the exam, let's ignore Simpson's rule. Okay, so What we're doing is we're recognizing that Taylor series is a mathematical tool that lets us figure out what the errors of these things and derive some of these formulas. This is where they come from all the way through. Okay, so hopefully that simplified that part of the lecture up a little bit. When we get to solving not just derivatives or integrals, we can apply this logic of approximating derivatives to solving differential equations. And this is where we got into the idea of what are called the Runge-Kutta methods. Euler's method, Euler-Richardson, are examples of a more general class of solvers called Runge-Kutta solvers or Runge-Kutta numerical methods. They are used for solving any differential equation, which is written in the form of the derivative is some function of itself and optionally time. This bit of code, this bit of math is just pointing out that we can start from this equation, use a forward difference, and what we come up with is something which is equivalent to the Taylor series. It's the same terms up to and including the delta t term, so we say it's first order accurate. This was basically the question that we had on test number 2. I wanted you to start with this expression and come up with this thing and tell me that it was first order accurate because it's equivalent to Taylor series. So draw a box around this. This is what we did on test number 2. This is a longer derivation. This is the one for the midpoint scheme for second order Runge-Kutta. This is too long to memorize. I can't really see myself asking this particular question on the final exam, so let me just take a look at it for a second. This one starts with the central difference, and we proved that it was a delta t squared sort of method. I think for the purposes of the final exam, yep, I can make a decision on that. Too complicated for me to ask that as a final exam question. I hope you agree with that and are okay. There are other schemes, though, that are based on things like the center difference that lead to more accurate schemes forward. One of them is called the midpoint algorithm, otherwise known as the Euler-Richardson algorithm. It's the idea that to approximate a derivative, what you can do is you can use multiple steps all the way through. I want you to know that this algorithm is second order. Why is it second order? Because if you did the algebra, you can show that it's consistent with the order t squared term of Taylor's theory. I think that's the important point all the way through. And then we also introduced another method called the fourth order Runge-Kutta method. And the only thing I'm going to tell you about that one is it's called a fourth order Runge-Kutta method because if you were to actually evaluate all these terms, what you would discover is it's consistent with and up to the fourth power of delta t in a Taylor series expansion. We didn't actually do that, nor will I ever ask you that on a final exam. You should know these methods enough to be able to implement them or recognize if they've been implemented incorrectly. And that's what I asked you in test number 2. I had you take a look at this code to find the mistake with it. I won't ask you that exact question again. It's a tricky question. I recognize that. Okay, beyond here, we had some worked examples where we wanted to talk about how these codes were set up. I don't think there's anything in particular that's needed from these examples. The lecture was really on the idea, the concept of these things. In lecture 12, we reviewed the exact same stuff again. Wow, it's all the same thing. I seem to have copy and pasted that lecture. Did I just copy and paste this whole thing? I must have. I have an extra copy here. I think I have lecture 12 twice. Do I have lecture? Yeah, there we go. That's why it's not right. I was wondering why this lecture was so big. Because this lecture actually starts here. There we go. That makes more sense. This was lecture 12. I was confused for a second why that previous lecture was so long. It wasn't that long. This was lecture 12. We talked about these different numerical methods. This was the lecture where I described for you by drawing diagrams, showing you the different steps. It is worth taking a moment and visualizing for yourself what this code actually means, how these steps link together all the way through. In terms of little facts, first order method, second order method, fourth order method. If I give you a method that's new, you haven't seen it before, you should be able to take an algorithm like that and turn it into Python code. In this lecture, we reviewed that we've now looked at a number of different physical systems. Here are examples of physical systems. Any one of these, or others, could be solved by any one of these different numerical methods. So the general idea here is given a numerical system, an equation that's written in the form of derivatives is equal to things, left-hand side is equal to the right-hand side, we can use any of these numerical methods to solve it. So what I was doing in this lecture was try to introduce the idea that this was even a more general concept. That rather than talking about specific examples, like air drag, or an oscillator, or a forced oscillator, we could just talk about a generic system. There are variables, and there are the derivatives on the right-hand side. If you have that generic idea, you can write a generic solver. And this is what we talked about, but state vectors. You can solve a whole class of problems at once if you just think about the functions on the right-hand side being defined, and you think about x, y, vx, and vy together representing a state of the system. That's what this note solve represents. Okay, there's lots of stuff there, but I'm going to leave that all the way through. I think this is pretty important, the fact that you can now write a generalized Euler stepper, and notice that what you're doing is you're evaluating the derivatives, that is the right-hand side of the system, applying Euler's method. Euler's method is take the variable x times its derivative times the time step. This is a state vector though. So you're doing this for a vector operation. You're doing this for all the x's and v's and vx's at once, in one go. And then what I did is I gave you an example of how to implement the right-hand side of this function all the way through. I have another example here for this system of equation and what this guy looks like. Again, it's not the specific equation. It's being able to go from this set of equations to whatever needs to go here so that you could actually solve the problem. So let's leave that in this notes, and I'll show you what a midpoint stepper might look like as well. Okay, I think all that is... Oh, there's an RK4 stepper. There you go. I think those are pretty good to leave in there because that sort of is a great review of everything we've covered up to that point. So you can solve general problems with these things. Okay, so we've now made our way through 2/3 of the course. I wonder if we should do something with polynomials. Yes, we should keep on persevering. So before I leave solving ODEs in general and the stuff on Taylor series, is there any questions or comments or points of discussion you'd like to have? Okay, continuing on. We talked a bit more about data analysis. Data analysis, the loading in of data, whether or not you type it in or you use something like read CSV. These were ways we loaded data in. And when we loaded data in, you need to be able to plot the data. You need to be able to do some basic kinds of fits. NP polyfit, NP polyval, I think are important things to understand how they work all the way through. In terms of an example, I'll leave this first example in there So just to review, the example is you have some data, it's in a data frame. Do you know how to plot it? Do you know how to do a fit of that data to some order? And do you know how to evaluate that data all the way through? This idea is not the way we end up doing it. We in fact want to use polyval to evaluate that whole set of coefficients all the way through. So I'll clean up these notes by getting rid of these blocks so they don't throw you off. Okay, so the coefficients are that. Here, we'll do this one. I think this is a better way of writing this code. Polyfit lets you fit any X components against any Y components. Horizontal axis, vertical axis, order of the degree. P is a polynomial. It's represented by all of its coefficients, and you can evaluate those polynomials against any set of X values. And we have another example and another example. Let's get rid of those other examples because I think they just confuse the issue. Okay, nonlinear curve fitting. I think this is an important idea to be aware of, that polynomial fits are not the only thing out there. There are other ways of fitting it. I asked you a question on this, a very small question. You all actually did very well on it on term test number 2. The important bit here, I think, what should we say? What should we say? How about this? Remember, in the future, one of the things that using something like optimized curve fit does is it's able to give you the error associated with the coefficients. As long as you've remembered that one tidbit of knowledge to be used later in your life, I'm very happy. And for the purposes of the final exam, let's just ignore everything to do with curve fit. Okay, so what I'm doing is I'm removing from these review notes anything to do with optimized curve fit. I want you to focus on polyfit and polyval and how they're used so that you can do fitting of any table of data, whether or not it comes in from a file, or it comes in typed in, or it comes in from a numerical model. These are all data frames all the way through. So here is an example of fitting some data. You might recognize this as being a center difference formula. Once we have a center difference formula, we can fit that data in different ways. So I'll leave that example in there because I think this is a good way of showing how all these parts work together. Okay, nearly where I want to get to, and I think this might be where I want to get to for today. This lecture ended with a little example on SciPy. We'll talk about SciPy again on Thursday. Its primary use in this course is to give us a way of writing down functions and evaluating the derivatives of those functions so that we can solve them numerically. That's primarily what SciPy was used for, but I'll go over that, I think, on Thursday, because there's something else I want to address before the end of the lecture. Okay, so what we've done is we've covered lectures 7 through 13, the next middle part of the course. On Thursday, we'll finish off the course with something on computer algebra systems and SciPy, and a little bit of the celestial planetary mechanics that we've done. One of the requests I had in the chat was, could we spend some time talking about the assignment? We have 15 minutes. Would you like to spend some time talking about assignment number 7? Cassandra says yes. Okay, we will spend a bit of time on there. I don't need to see it till the end of Wednesday, but I want to make sure that this is straightforward. It's a good example of SciPy anyways. So let me just go to assignment number 7. Okay, so first thing I'll note that my due date isn't till Wednesday evening. I'll take Thursday afternoon if you really need it to in terms of doing it. Like it's got to be done before the end of the week, obviously, but I will mark it as soon as I get it. I'll post the solutions for this at the end of Friday. So if you need one more day even, don't worry about it too much. I'd rather you do it as opposed to not. This is a problem which is building off of what we did with planetary motion. The idea that forces can be described in terms of derivatives of potential energy. This idea of derivatives of potential energy, the whole idea of work, is something that occurs for conservative forces. We did cover this in Physics 1050. So here is a kind of force with a potential that's given by this function. This is a Leonard-Jones potential. All that it's saying is if you have two particles that are separated by a distance of r, that's enough information to tell you what the potential energy of that two-particle system is. If you have a potential, you automatically have a force by taking the negative derivative of that potential function. That's what a force is. I want you to solve this problem. So the idea here is to follow the same structure as in lab number 6. So I'll give a couple notes here. Okay? Follow the same structure as found in lab 7. Okay? So you all did lab number 7. 7 had no problems at all. But the idea here is you're going to start by implementing U as some SymPy function. Okay? So U is going to be equal to some SymPy function. It's an expression. Okay? So it's an expression of SymPy in some sort of way. Once you have that, you can use SymPy things to calculate its derivatives. Now here's the trick. If I want to figure out what Fx is and Fy is, the forces, F of x and F of y, I'm going to be able to write those down as NumPy functions if I lambdify the coordinates involved. Remember that a potential is the potential between any pair of coordinates. So if you take any pair of coordinates that are described by the components x1, y1, x2, y2, this set of components is enough information to figure out the force between those two things. If I already have some expression U, then I can just say minus U, the derivative with respect to x1. This thing will be force on particle 1 by particle 2. When you take the derivative of x1, that's going to be that component in the x direction. And that's the important part here. Pair of particles, you're going to get that structure. You can do it not only for Fy, you can also do it for the y component. For this to work, you're going to have to write r in terms of x1 and y2. So that's the first big idea. The second big idea is to think about the equations of motion. Okay? So I want you to remember that one of the things you've been doing is you understand F equals ma, where F is the net force. Okay? So if you're going to, why didn't we do x3? Because the potential is between any pair of particles. Okay? Given two particles, the force between the two of them is given. So Fx evaluated, okay, is the force of x of 2 on 1. Okay? Okay, here's the important bit. This same function is the force of whatever on whatever. If I need to figure out what the net force on 1 is, it will be equal to the force of 2 on 1 plus the force of 3 on 1. That is to say, Fx1, the net force in x on respect to 1 will be equal to this component plus this guy. Can you see how, well, I haven't defined them, but can you see how what we're doing is we're defining this? We're using the same functional form, but what variables we pass in, that will give us a certain value. If I wanted to figure out what the force of 1 on 2 is, okay, well, the force of 1 on 2, this would work. Okay, that would be, that's correct. Okay, that's another way of writing down those forces, right? If you want to force the force of particle 2 on particle 1, another way of thinking about it is the negative of the force of particle 2 on particle 1 for any 2 particles. So 3 on 1, 2 on 3, 1 on 3, 2 on 3. There's like 6 different ways of talking about it. It is helpful to take some scrap paper and make a drawing. Make sure you got all the forces. Every particle is going to feel 2 forces from which nearby. The only other complication in this question is, I'm going to say this. Remember, it is F1 equals M1 times A1. F2 equals M2 times A2. Okay? These masses don't need to be the same even if the forces are the same. So in a 2-particle system, right, if you have 2 things, say, remember we did this thing, F net on the sun, right, this will be equal to the force, like when we did the planets, planet on sun, and the net force on a planet is equal to F of the sun on the planet, this idea of looking at equations. That's the same as the negative of the force of the planet on the sun. But when you go and you take those equations and you turn them into the acceleration of the sun, that's going to equal to the force net on the sun divided by the mass of the sun, right? Which almost always is going to be equal to 0 for the planetary problem, but it's not equal to 0 if this mass isn't tiny. So the point here is make sure you get the masses in there as well. Okay, so my point is, to solve this problem, you need to implement some functions f of x. Use SymPy, starting from here, to calculate the derivatives, to calculate what those functions are. Write out equations of motion, okay? Actually write out for yourself, like I've done many times, derivative of x with respect to t is equal to f net 1, f net 2. And then write lines of code that figure out or calculate what the components are of the force. That's what goes inside of a stepper. And I want you to solve that whole system using the midpoint method. You have in the lecture already the framework of how to solve any dynamical system using the midpoint scheme. Is that enough information to let you finish off assignment number 7, or is there something you'd like to clarify? The question is, when's the actual due date? It's due then, let's say, okay, fine. Do you need more time? If you're done, just you're done. But I don't want anyone to not complete this question. What's the date of Friday? The 27th is tomorrow, 28th, 29th. Is that okay? Let's go with that as the final due date, and my Friday afternoon will be spent marking these and posting them back. Okay, there was another question for, are you going to be posting a sample final? I did. So, this is the final I was using last year. I haven't posted the solutions, but you know what? I will. I'll post the solutions right after this lecture as well. But here's the thing about this final exam. That final exam was based on a previous version of the course that didn't have 100% of the same style as this course. We didn't have the idea of a stepper and an app and a plotter. So the questions are asked slightly differently. Don't let that confuse you too much. And it was also designed to be done on the computer as opposed to by pen and paper. So with that caveat, I will post that solution. Okay, question about the assignment. Is it okay if we assume M2 stays stationary since M2 is bigger than M1? No, it is not okay. All 3 particles are going to move. Yes, M2 is bigger than M1, but it's not 1,000,000 times bigger. It's like 10 times bigger. If things are 1,000,000 times bigger, sure. But these things aren't so big. They're 3 similarly sized objects. So let 3 things move. Anything else that we could talk about for a minute on this course, as my battery is about to die? Oh, there we go. Of course, same rules. 1 sheet of paper, front and back. Anything you want to put on there, be my guest. And if you want to use the computer to help you write it, that's fine too. That seems totally fair to be able to bring that in. So on Thursday, we'll finish up the review of the lecture material. There isn't actually that much more because a lot of that was worked examples. I will talk briefly about the labs and the assignments. And I'll just go through any questions that I think are useful to study and any questions that are not useful to study. And then we just need to talk about when and if you'd like me to host office hours or another review session or anything like that. Anything else for today's lecture? Okay, sounds good. As before, if there's anything that you want to communicate to me and you'd rather say it to Kyle so he can tell it to me, that's totally fine. Otherwise, I will get this lecture posted onto YouTube, get the last one posted on YouTube, post some things, and can continue to give you feedback on stuff. Okay, have a great afternoon, everyone. All good? Thanks very much.